This colloquium is being organized by the Indian Physics Association as a part of online monthly colloquium on recent development in scientific research in physics. I would now like to request Professor Chari, Director of IISER Berhampur, for a welcome address and for a brief introduction about our institute.
Thank you, Natasha. Can you just allow me to show one slide? You have to permit me to share my screen.
Yeah, I think you can do it now.
Yeah, I'm able to do that. Yeah. Are you able to see this?
Yes.
Yes.
Yeah, particularly those who are not in a position to, those who do not know our geographical location of our campus. I just wanted to show this slide, and I'm sorry if I'm taking some time. And we always take pride in showing this master plan of our campus.
No problem. Sorry to interrupt you. Please take your time.
Yeah. So we are building an integrated self-sustaining campus, which has all the signatures of the 21st century. And this integrated built form seamlessly merges the disparate disciplines into unified structure. And what you see here, I don't know whether you are able to see my cursor. And this is going to be a single academic block, which is coming up, which is going to house all the people under one single roof. And the motto here is to create interaction and creativity among different disciplines. And here on this side are going to be the hostels, which are going to house 2,000 students. And here we have this residential complex, actually. It is akin to, I should say, TFR, which is on banks of Arabian Sea, and we are right on the banks of Bay of Bengal. And our boundaries is just 60 meters away from the high tide. Having said that, I should just give a glimpse of our vision and mission. And my dear friends, I'm delighted to be part of this virtual colloquium. The Indian Institute of Science, Education and Research is poised to expand and diversify its mission of carrying out science education and research of the highest quality based on an integrated view of modern science and training young students to address the challenges of the 21st century. The vision for the IISER Berhampur campus is based on an integrated view of modern science, springing from the priorities and aspirations of our nation today. The institute seeks to develop a teaching, a research, and a residential campus that will set the new standards of sustainability, function, and aesthetics, and will provide an environment that fosters interaction and creativity, as I have shown with this master plan a few minutes back. This structure envisaged is akin to that of a research university with a total project cost of 1,500 odd crores in rupees. In its nascent years, science at IISER Berhampur will focus on education research themes chosen within and across the departments of biological, chemical, mathematical, and physical sciences. And very soon, I think from this year onwards, we are also focusing on even computer science and earth and environmental sciences. Each of these themes is of great contemporary importance, and IISER is well placed to develop them on a significant scale with high impact. Importantly, these themes have close interconnections with each other and are closely linked to areas which are critical for India today. whether you call it as communication or energy or health. The ultimate scale of the IISER Berhampur campus is set by size of the academic faculty, which is envisaged to reach a steady state figure of 200 on a time scale of about 10 years from now. Concomitantly, it is planned to have around 2,000 students on board. Also, there would be a large population of research scholars pursuing PhD degrees and vigorous visitors program to host faculty and researchers at all levels, including project students and even interns. An important objective of the new campus is to enhance IISER Berhampur's contribution to the pool of highly skilled scientific manpower in the country manifold to meet the scientific and research challenges in the country. Several of research areas planned will have a synergy with the programs within the units of the Ministry of Education, as also with other institutions in the country, whether it is TFR, Ministry of Science, or BARC of that kind, and would land and lead to strong collaborations. Further, a linkage of research performed in the IISER campus with potential applications will be built from the start to benefit the country as a whole. Thus, we envisage to create a campus that is of international repute, that will foster a mutually beneficial faculty-student relationship through an integration of science education and research that will augment the national capabilities in all areas of science, and that will provide a large platform for acquiring the fundamental knowledge in science that is essential for generating technological know-how that society needs. If any one of you in the audience wish to be part of this journey and evolution, please do write to us and we'll respond immediately. Thank you for your kind attention, and I wish you an exhilarating colloquium.
Thank you, sir, for your kind words and enlightening us about our institute. Thank you. Now, I would like to request Professor Vandana Nandal, General Secretary of Indian Physics Association, to say a few words about the IPA and also about its activities. Over to you, ma'am.
Thank you, Natasha. First of all, thank you to IISER Berhampur for hosting this colloquium and giving IPA an opportunity to co-organize this colloquium. So a few words about Indian Physics Association. IPA was founded in 1970 with a goal to help the advancement, dissemination, and application of the knowledge of physics. It achieves it through arranging various special lectures, programs, publication of bulletins, reports. The idea is actually to bring the science and the excitement at the forefront to the students and young researchers and teachers. Some of the IPA lecture series are the DAE CV Raman lecture series. We organize 5 lectures by eminent scientists every year. IPA also liaises with other international societies like APS, American Physical Society, Institute of Physics UK, and with UK it has and the AAPPS, that is Association of Asia Pacific Physical Societies. With IOP UK, we have an exchange lecture program, which is on alternate years. The scientists from India travel to UK, and from UK they travel to India on the next year. And in India, this series, the lectures are called Cockcroft-Walton lectures, and in UK, they are called Homi Baba lectures. This year, due to travel restrictions, they are still prevailing in some parts. The program will be online, and this will be an webinar, Cockcroft-Walton webinar, centered on COVID-19, trying to figure out what we learned from it and how what we have learned will help us in dealing with pandemic-like situations. The IPA also partners with various sponsors, various conferences. We ran a webinar series, New Horizons in Physics, to commemorate Golden Jubilee of IPA, and this entire, all the lectures which IPA has organized in the last 2 years are available on the YouTube channel of IPA. In addition, IPA gives awards to senior and young scientists in recognition of their contributions, and the announcement requesting nominations for IPA Awards 2022 have been just made out, and please visit our webpage for more details or write to us. The present office bearers are Professor Ramkrishnan, Director TIFR, is the President of IPA. Professor Tanushree Dasgupta, Director SN Bose Center, Kolkata, is the Vice President of IPA. Myself, General Secretary. Professor Samit Mandal from Delhi University is a Joint Secretary. Dr. Aradhana Srivastava, BRC, is Treasurer. And IPA, a few years back, has established a gender working group to address the issue about gender equality in the physics profession in India. And Professor Shubhapati Goswami, PRL, is the chair of the IPA gender group. So if you want to join IPA, please visit our webpage and you can go to the registration, request a membership. The form can be filled, it's completely online, needs to be forwarded by one of the IPA members. But do let us know if you have any problem and you would like to join that. If you have any issues, please send a mail. I'll put this also in the chat box. So in this, I forgot to mention the IPA also brings out the quarterly news bulletin Physics News, which is completely available online. In the last year, IPA organized 2 webinars with APS. One of them particularly was aimed at young researchers for the orientation for young researchers publishing with APS. This is also available on the IPA YouTube channel, and one was on the gender issues. So what new things we can learn about gender equality. In the IPA Colloquia series in the last year, we have had several interesting talks by many scientists, and today's talk also is going to be given by one of the very, very talented young scientists, Dr. Suratna Das, and you have seen this poster. So now I will just hand it back to your host, Dr. Natasha. Thank you, Natasha.
Thank you, Professor Vandana, for giving such a nice introduction. Now, moving on, I would now like to give a brief introduction about Dr. Suratna Das. Dr. Das did her PhD from Physical Research Laboratory, PRL, Ahmedabad. She did her postdoc from Tata Institute of Fundamental Research, Mumbai. After that, she joined IIT Kanpur as an Inspire faculty. Very recently, just last year, she joined Ashoka University as an assistant professor in physics. Her main area of research is cosmology and astroparticle physics. It is our privilege to have Dr. Das as speaker today. The title of her talk is What is Troubling Cosmic Inflation? I'm sure that our young minds, especially the undergraduates and the research scholars, will gain a lot from today's colloquium. Over to you, Dr. Das.
So I'll start by thanking Professor Vandana Nanal for inviting me to give this colloquium. She invited me to give this colloquium in April, but as I was teaching during that time, I was quite busy, and so I requested her to postpone my talk, and so I'm having it now. And I also like to thank Professor Natasha Sharma and Aizar Behrampur for hosting this talk. I'm really grateful to the Aizar Behrampur for hosting this talk. So let me share my screen. So can you see my screen now?
Yes.
Okay. So can you see this screen moving?
Yes.
Okay, good. So so my today's talk is what's troubling inflation. So first of all, even if you don't find this word inflation in a physics book, you can very easily find this word in day-to-day newspaper, right? So if you read newspaper, then this word is, you'll get very familiar with this word inflation. So inflation is a very well-known word, but when we read that word in newspaper, we actually talk about economic inflation. And economic inflation is not a very soothing thing to us. It actually devaluates the purchasing power of money, and it causes a lot of trouble to our day-to-day life. The prices of groceries goes up, the prices of interest rates goes up. So inflation in economics is a bad word. So reducing inflation is something which is the aim of a good economy. But so inflation causes a lot of trouble in our life. But what can cause inflation, trouble to inflation? So when I talk about inflation, I talk about something which are known to physicists. So this is not economic inflation, but this is this is something related to physics. And so you can see this young guy which has come to his grandma saying that physicists had discovered definitive evidence of inflation. And the grandma didn't knew about the physics of inflation. He said, so ultimately the scientist has probably gone and bought their groceries from the market. So they can see that inflation is there. But no, so this is not economic inflation. Today we'll be talking about what is known as cosmic inflation. So this is a part of the Big Bang universe and how our universe has evolved. So, sorry, my screen is not moving. Okay. So this scientist is explaining this normal guy about how life has come to existence in a universe. So he first says that on that signal in the sky, we can trace our origin. We were light once. So we started with very high energetic particles and basically photons, and we see a bath of photons all around us that we know as cosmic microwave background. And there were ripples in the cosmic microwave background. And that ripples finally became stars and galaxies and matters that we see around us today. And that has given existence to the life we know as today. So everything depends on these ripples, and these ripples have been caused by cosmic inflation. So the cosmic inflation play a very major role in the evolution of the universe. Without those ripples, nothing could have been formed in the universe. So cosmic inflation is actually a very important phase of the evolution of our universe. So when I say what's troubling and inflation, I actually mean what's troubling cosmic inflation. So I'll show you that inflation is very necessary, but there are many things that we still don't know about cosmic inflation. This is not a very old field of physics. This is only 30 years old, but many work has been done in the field of inflation, but still there are many open questions that one needs to address in cosmic inflation. So let's start our talk. So this is a very well-known picture of how our universe has evolved from a very the initial singularity, which is known as the Big Bang. And since the Big Bang, the universe is expanding. So when the universe expands, what it does is that it cools down. That is one feature that one can always have in mind. But just after the Big Bang, when the age of the universe was only 10 to the power minus 36 seconds, the inflation has gone through a rapid expansion. So it was expanding, but the rate of expansion became accelerated. And that happened for a very small period of time. And this period is known as inflation. Okay. So this is the period which we will talk about most in this talk. But after that, after inflation, so inflation is a very brief period of time when the universe had gone through a very rapid expansion. Why it is needed? Because then a causally connected region from the early universe actually became inflated, and that inflated region is the whole universe that we see around us today. Okay. So after this inflation, the universe entered a radiation dominated era. At that time, the temperature, why we call this era as a radiation dominated era? Because during that time, the universe was so, the temperature of the universe was so high that all the particles were there in an elementary form and they were all treated relativistically. So the energy of the particles were very high, the universe was very hot, and we call this as a radiation dominated era. So because we do treat these particles relativistically. And we can see that during this radiation dominated era, when initially the particles were all in the elementary form, so we can see that LHC protons can be probed when the age of the universe was 10 to the power minus 10 seconds. But when the temperature, when the time was 10 to the power 2 seconds, that means when it was on nearly 3 minutes of time, then first the nuclei started to form in the universe. Before that, there were no nuclei. It were even in a much more simpler form or in a much more elementary form. So the first nuclei in the universe formed when the age of the universe was nearly 3 seconds or 3 minutes of time. Okay, but after and as you can see that the Big Bang model explains a universe which is expanding, so it keeps on expanding, and when it keeps on expanding, the temperature of the universe keeps on decreasing. So at some point of time, the temperature drops so much that the matter in the universe become non-relativistic. So we don't treat the matter in the universe relativistically anymore. We will treat the matter relativistically. We start treating the matter non-relativistically. And at that time, the universe entered a matter-dominated phase. And during this matter-dominated phase, something very remarkable happened. That is the formation of the cosmic microwave background. What happened at that time? That this is the time when the first nuclei first atoms start to form. So there were protons and there were electrons in the cosmic plasma. They try to come together and try to form neutral hydrogen. But before that, the energy of the photon was so high that the photons can knock out the electron from a bounded hydrogen atom and can break off that atom. So hydrogen could not have formed before this era, but here the temperature of the universe had gone down so much. So you know the binding energy of hydrogen is 13 electron volts, 13.6 electron volts. And so the temperature of the photons have gone below 13.6 electron volts. So the photons do not have enough energy to interact with the neutral hydrogen atom to break them off. So neutral hydrogen could form, and the whole universe become electromagnetically neutral because all the protons and all the electrons came together and formed neutral hydrogen. So the photons, which could only interact electromagnetically, could not find any electric charge to interact with. And at that time, the photons, because it could not any longer interact electromagnetically with the cosmic plasma, they decouple from the cosmic plasma. And these photons actually then started free streaming towards us. And this is what we see today as cosmic microwave background. Okay. And the key point is that, so in the cartoon, we saw that this photon bath had ripples. And that ripples grew to give us stars, galaxies, which we see around us today. And these ripples were caused by inflation, which happened 10 to the power minus 36 seconds of when the age of the universe was only minus 10 to the power minus 36 seconds. So the signature of inflation was imprinted in the CMB, which formed when the age of the universe was nearly 3 into 10 to the power 5 years. That is a remarkable observation which had been made in 1980s when inflation was first proposed. And we will see how we can probe this signature of inflation in the cosmic microwave background. Okay, so what we see in the CMB. First of all, CMB was first discovered in 1965 by Penzias and Wilson. You must have heard this story, how this cosmic microwave background was first discovered. So Penzias and Wilson were trying to, this was the experiment that this is a radio antenna, and they were trying to observe some galaxies. But when they formed this, created this antenna, they were seeing a noise throughout the sky. And they couldn't get rid of the noise by doing whatever means they had at that time. So the noise was uniformly there throughout the sky. And they were very puzzled and they could not understand that they were seeing the cosmic microwave background. So there were people from Bell Lab there then who confirmed that they are actually seeing something of very great importance, which has something to deal with the universe's evolution. And that time they realized, Penzias and Wilson realized that they have seen something of big importance. And in 1978, so this is an accidental discovery. They were not trying to discover the cosmic microwave background. They were trying to see something else, but accidentally they came across this cosmic microwave background. And for that, in 1978, they received the Nobel Prize. So this is a very remarkable story of finding cosmic microwave background, which was actually an accidental discovery. It was not meant to be discovered. People were not looking for that cosmic microwave background at that time. But Penzias Wilson, it was their sheer luck that they came across this and they win the Nobel Prize in 1978. So because the antenna was not sensitive enough to recognize, go beyond this uniform temperature, there were theorists who predict that this temperature should have some fluctuations of the order of 10⁻⁵. So this temperature is 2.73 Kelvin, and the temperature fluctuations were of the microkelvin level. And to measure this the temperature fluctuations in the CMB, in 1992, there was one experiment which was a satellite which was launched, which was named Kobe, and they found this temperature fluctuations in the cosmic microwave background. So in the microkelvin level, so you can understand the sensitivity of the level of that experiment or the satellite that was launched at the time. And in 2003, another satellite was launched, which was named WMAP, Wilkinson Microwave Anisotropy Probe, and they measured they confirmed that the CMB actually has fluctuations, and they measured the fluctuations at a much more precise level. So for discovery of the cosmic microwave background, after confirmed by WMAP, the two leaders of Kobe, Matter and Smoot, got their Nobel Prize in 2006. Okay. So this is the discovery of cosmic microwave background, which is one of the cornerstones of modern cosmology today. And so what we know about, so you can see this, how precise the measurement has gone over the years. So Kobe, this is the precision of perturbations that they could have seen on the CMB sky. WMAP done a much better job. So this is how they map the sky. So you can see the perturbations are now much more clearer. Here it was quite hazy, but WMAP had clear signatures of cosmic CMB temperature fluctuations. And Planck, which is an even more recent satellite, it has actually seen the CMB sky in a much more greater detail. And this is how the CMB sky looks today in the present form. So we have actually probed the CMB sky with much more precision. Okay. But the CMB photon not only has fluctuations in its temperature, the CMB photons are also polarized. We can see the polarization patterns on the CMB sky. If the patterns are mirror image of each other, we say that they are E modes. And if they are antisymmetric, we call them B modes. These E modes are created by, we will come to it, by the scalar perturbations of this during the inflation. And the B modes were created by the tensor perturbations in the early universe during inflation. Okay. So what we actually, so just to summarize what we know about the CMB. So this is the Kobe observation of the CMB background sky. So this is the 2.7, the uniform temperature throughout the sky that we Penzias and Wilson had seen. But these dots are the points with error bars. So these are the actual error bars. And this solid line is the fit of a 2.725 Kelvin blackbody spectrum. And this, you can see how nicely the observations fit the blackbody spectrum so nicely. So we can see that the temperature of the CMB is very precise over the sky, which is 2.725 Kelvins of a blackbody spectrum. And the temperature fluctuations are measured as a correlators. So we can see a temperature fluctuation on this side of the sky, then we see a temperature fluctuation on another side of the sky, and we measure the correlations. And because we are seeing this CMB fluctuations over a spherical sky, we decompose these correlations into spherical polar coordinates. So this L on the x-axis are the multipoles, and these are the 2-point correlation function of the CMB sky. Okay, so these dots are, you can see, these are the observational points from the Planck satellite, and these are with error bars. So you can see beyond this scale where the error bars are large, after that scale the error bars are quite small. And this is actually prediction of inflation, this red line, which is fitting the data. So the fluctuations, so inflation predicted that there would be fluctuations in the CMB, and this red line is the fitting curve of that thing. So you can see how nicely it fits. So the prediction of inflation is quite precise. And then these are the polarization graphs. So this is the temperature correlation, which has been shown here. This is the temperature E mode correlation. This is the E mode correlation, and this is the B mode correlation. So you can see that the temperature correlation has the highest amplitude, and as we go to the correlation of the polarization, the amplitude drastically reduces from the temperature thing. So let's talk about inflation. So because these are the so these feeds are from inflation, so we should know how inflation predicts this kind of a fit. So first of all, we should know how our universe has evolved theoretically, and this has been governed by the Einstein's general theory of relativity. So what Einstein's general theory of relativity tells us is that this is how this g mu nu equal to 8 pi g t mu nu, it looks very complicated, but this is how a space-time of a universe should have evolved. So this g mu nu is known as the Einstein field tensors. So this part tells how the background space-time universe evolves. The space-time of the universe has evolved. So this g mu nu is the dynamics of the space-time of the universe, and in the for the evolution of the universe, the background metric is governed by the Friedman-Robertson-Walker metric, and this is just looks like a flat space-time metric, just like a Minkowski metric, but there is a time-depending factor sitting in front of the space. This time-depending factor is known as the scale factor, which says that the space is evolving with time. So you can see, if you can recollect the picture of the Big Bang universe that I have shown, that it starts to expanding since the Big Bang. So this expansion is taken into account by the scale factor. Okay, and during inflation, the expansion was accelerated, and it was almost an exponential expansion. So this is called the scale factor, and during inflation, this scale factor was exponential. This h is called the Hubble parameter. Okay, and what drives this kind of exponential expansion? So this is governed by the right hand side of the Einstein universe. So what the Einstein universe tells us is that the g mu nu is coupled with t mu nu. So that means the geometry of the space time is coupled to the matter content of the space time. So whatever the matter is there in the universe, that governs how the dynamics of the space time would evolve. Okay, so this t mu nu is during inflation, because it has to drive the universe to an exponential expansion. This can be done by a slowly rolling scalar field. No other matter can drive a drive a universe to expand exponentially for a very brief period of time. So this is a kind of dynamics which is required to drive the inflation, to drive the universe to expand in an exponential fashion. And this is the dynamics of the scalar field. By slowly rolling, I mean that the universe has a very flat potential, and the kinetic energy of the scalar field is so small that it cannot roll very fast. It is rolling over a very flat scalar potential, and the flatness of the scalar potential is defined by these slow roll parameters. And then Sorry. Yes. So we need a scalar field, which is a quantum field, to drive the inflation. Okay. And so I hope I have given you the message that the geometry is FRW geometry, but it is exponentially expanding during the inflation. And the exponential expansion was driven by a slowly rolling scalar field, which is known as the inflaton field. Now, this, as I said, this inflaton field is a quantum field. So it do not only have a background field, but it also have tiny quantum fluctuations in it. Okay. So if there is a fluctuation on the if there are fluctuations in T mu nu, then as because T mu nu is coupled to G mu nu, it will induce perturbations in G mu nu as well. So this is the whole point that I would like to raise, that this quantum field, the inflaton field, has quantum fluctuations, and these fluctuations would seed fluctuations in the background geometry because the T mu nu is coupled to G mu nu. So G mu nu is a metric, so it is a tensor, it is not a scalar. So that will induce perturbations in delta G mu nu, capital G mu nu. So this is the metric, and as you perturb the metric is a tensor, so it will have all kinds of perturbations. It will have scalar perturbations, vector perturbations, and tensor perturbations. We do not care about the vector perturbations because they decay during the inflation and they do not play any important role. But the tensor perturbations are of quite importance. They give rise to primordial gravitational waves, which has not been yet observed. And they also give rise to the BB mode polarization of the CMB photons that I have talked about earlier. But the CMB scalar the scalar perturbations during the inflation is of primordial importance because these scalar perturbations actually gives rise to the temperature fluctuations in the CMB that we see. Okay. So there are two kinds of scalar perturbations in the early universe. One coming from the T mu nu part, which is the inflaton field scalar perturbations. But there will be scalar perturbations in the metric as well, as I have said. So there will be perturbations in the metric, scalar perturbations, which is denoted by this small phi. So there are two kinds of scalar perturbations during the evolution of the universe during inflation. And we study them in a gauge invariant manner, which is known as the co-moving curvature perturbations, curly R. And this is the metric perturbations, and these are the scalar perturbations. So, and H is the Hubble parameter that I have already defined. Phi dot is the kinetic term of the scalar perturbations. Okay. And what happens during inflation? That during inflation, this is a de Sitter kind of a space. So the horizon, the causal horizon of the universe remains constant. H is a constant, so the causal horizon remains constant. But the scale factor, as because everything is evolving in an exponential manner, all the scales inside the universe would be stretched in an exponential factor, with an exponential factor. So wherever there is a perturbation inside the horizon, they will exponentially expanded within some time and they will go outside the horizon. So they, once the sub-horizon mode will become super horizon very soon. And the advantage of treating these scalar perturbations in a gauge invariant way like this is that this R is not evolving on a super horizon scale. So the evolution of R is 0 on super horizon scales. So we can treat, so on super horizon scale, the space-time is not causally connected. So this is a nice way that it does not evolve in the space-time where it is not causally connected. So we do not care about the evolution of R on causally on super horizon scales, and we can only look at their dynamics in the sub-horizon space, and that is all. But once inflation ends, the Hubble the radius of the Hubble parameter starts to expand, starts to grow faster than the modes. So if the Hubble radius grows faster than the modes, then the modes will, which were there on the super horizon scales, will start to come inside the Hubble horizon. Okay. So during radiation and matter dominated era, all these metric perturbations which were there outside will start to come inside the horizon. And there were perturbations on the G mu nu, which was seeded by inflation. Now that G mu nu will get coupled to the radiation and matter and will start to seed perturbations in the radiation and matter. Okay. So in the radiation and matter dominated era, T mu nu will get perturbed because the G mu nu was perturbed because of inflation. So inflation actually seeds this perturbations in G mu nu through the perturbations of the inflaton field, and those perturbations will get transmitted to the radiation field and the matter field at the later stage. Okay. So if there are perturbations in the CMB sky, these are the perturbations we see today on the CMB sky, that correlation function that I have shown you before. And the perturbations in the matter field actually seeds as the structure of formation of the galaxies and cluster of galaxies that we see today. Okay. So we can see that the scalar perturbations, these are the scalar perturbations during inflation, are somehow related to the perturbations of the CMB that we see today, because these are the seeds of the perturbations of the CMB sky. So the perturbations in the CMB, so I have told you that we study the CMB fluctuations as a 2-point correlation function. So we have to somehow calculate the 2-point correlation function of the inflationary perturbation as well. That is known as the power spectrum. And this power spectrum is now related to the CLs that we see today on CMB sky. And these are the transfer functions which encapsulates all the physics that goes beyond inflation till the CMB is formed. Okay. So this is this comes from inflation, and this is what we see today in the CMB sky. So now I hope this is clear how inflation seeds its signature in the CMB sky that we see today around us. Okay. But the thing is that this inflation has many models. And this is not a exhaustive list of existing inflationary models. And as you can see that so many models can predict the 2-point correlation function of the CMB sky we see today. And this is not quite good because it says that we actually don't know anything about inflation, because there can be so many models. So inflation is not yet a theory. This is actually a paradigm. But you need not have to go through so many different kind of models. If you have a very simple single field model, just one scalar field with canonical kinetic term, which is slowly rolling its scalar, its potential, then only you can fit this observation very well. You need not have to go beyond that. Okay. So this is the nice thing about inflation, that as a paradigm, it is very good. But the thing is that there are too many options for us left. Okay. So what is the problem with inflation? So first of all, as I have tried to motivate you, there are too many models and too less observables. So this is an observational issue. So the experimentalists should go and try hard to observe CMB in a much better way, so that there would be more observables that can be available for us to fit the models, and that can rule out many models. But this is not a problem of a theorist like me. For a particular for a theorist, there are many other problems to be addressed, and there are many theoretical issues. First of all, what is this inflaton? We have seen the standard picture of standard model of particle physics. There is no particle called inflaton. So what is this inflaton? That is a question. Also, there are questions, what can have happened before inflation? We don't know. We still don't know what had happened before inflation. Was there a matter dominated era? Was there a radiation dominated era? Was there something else? We really don't know. Can we actually see any signatures of inflation, of pre-inflationary era in the CMB? That is still an open question. And now we have inflation, but can we go beyond slow roll? Can there be any other phases? So for slow roll, I have told you that the potential of the inflaton field has to be very flat. Can there be any other option so that we can go beyond slow roll and can still have inflation? We don't know. Can there be alternative to inflation? Can there be any other scenario through which we can generate this kind of perturbations which can very easily fit the CMB power spectrum? We still don't know. But there are alternatives, and I have worked on this alternative. So these are my works which I have listed here. So these are the open questions of inflation and some of the works that I have tried to address these questions. And also there is a graceful exit problem. So inflation is an exponential expansion. So if you expand exponentially the universe for even for a very brief period of time, it will dilute all the matter contents of the universe. It is exponentially expanding. So very small patch will exponentially expand and all the matter content will exponentially dilute away, right? So there won't be anything left after the inflation. So after inflation, you have to gracefully stop inflation and start radiation dominated era. This can be done in a very nice way in a standard inflationary model, but there are other alternatives to inflation known as warm inflation. So I have shown in this paper that graceful exit problem is not so simple in that kind of inflationary models. But will not go into the details of this kind of models. Okay. So these are existing theoretical issues, but there are conceptual issues as well. What are the conceptual issues? What should be the initial condition of inflation? So inflation to start with should have made some initial condition so that inflation could begin. If those initial conditions were not met, the universe might not have gone through an inflationary phase. So those initial conditions were very crucial, and it is a very long debate which cosmologists like to go through. And this is not yet known very well what should be the initial conditions of inflation. The major problem, the major conceptual issue which I'd like to highlight in this talk is the quantum to classical transition of primordial perturbations. So I said that inflation is solely responsible for all these perturbations in the CMB sky or in the matter dominated era, which later on grows to galaxies and stars and all that thing. But these are all classical perturbations. However, when the perturbations were seeded by inflation, inflaton field, those were quantum perturbations. So how these quantum perturbations evolve into classical regime? That is a big question that cosmologists debate over the ages, and there is still no conclusive results, and many cosmologists differ in their opinion. Okay. And there are swampland conjectures and some problems, other problems like transplanckian sensitive conjecture. So this comes from string theory, but because this is a pedagogical talk, I'll not like to go into much more detail of this issues. But let me highlight this problem. So I hope that the audience are acquainted with quantum mechanics. So this is very close to quantum mechanics. So I'd like to elaborate on this problem. Okay. We all know that in quantum mechanics, there is a measurement problem. What is a measurement problem? A measurement problem is that to measure something in quantum mechanics, we need to have an observer. Some observer has to observe something so that the wave function can collapse and we can observe the quantum mechanical system. So this is a measurement problem. So as you can see from this slide, so there is a question: does quantum theory describe an objective reality independent of the observer? If there is no observer, can we still have a quantum mechanical system? So it was Bohr who said that no, it cannot be done. You really have to have an observer so that we can observe something and then the wave function can collapse. So the collapse of wave function is highly dependent on some observer, some person with consciousness, so that they can actually observe with a conscious mind a quantum system and the wave function can collapse. This is quite bizarre. So there are more realist scientists like Einstein, David Bohm, and Everett, who said that no, quantum mechanics does not require any observer. you can go beyond that and you can do your measurement and the thing. Quantum mechanical observations may not depend on the observer at all. It can be on their own as well. But the whole point that there should be an observer or not is redundant in cosmology, because in cosmology, when things were becoming classical from quantum regime, there were no observer. There were no person of the conscious mind which were doing the observation. So what was going on? So this question itself is a very bizarre question, that whether you require an observer or not. So in cosmology, there is no observer. So what is going on? So this is even a even more deeper question to quantum to classical transition is a deeper question in cosmology than in a tabletop experiment. Because in tabletop experiment, you actually have an observer. You actually have something which is observing the system. But in cosmology, there is nothing. Okay. So as our great scientist Steven Weinberg has said that in his book, he wrote in his own words that my conclusion is that today there is no interpretation of quantum mechanics that does not have serious flaws, and that we ought to take seriously the possibility of finding some more satisfactory other theory beyond quantum mechanics, to which quantum mechanics is merely a good approximation. So a scientist like Steven Weinberg thinks that the basic quantum mechanics is not a complete theory and we should go beyond quantum mechanics. Okay. So the question of quantum to classical transition of primordial perturbations, we can approach this problem in two different ways. One is to retain the quantum mechanical dynamics intact and try to explain the quantum to classical transition problem. And this is the first option. So this is like talking about decoherences and Bohemian mechanics. But the problem with decoherence and Bohemian mechanics is that you do not modify the quantum mechanical system, modify the dynamics of the quantum mechanical system. So this decoherence or Bohemian mechanics cannot have any observational signature. So even if decoherence or Bohemian mechanics are playing any importance role during the early universe, you cannot conclusively say whether these are responsible for any kind of macro objectification of the primordial perturbations or not. But there are other models like collapse models where you can actually go and modify the quantum mechanical mechanism or modify the basic mechanism of quantum mechanics. You modify the basic Schrodinger equation. And once you modify the Schrodinger equation, the wave function would start to evolve in a different way. And that will leave some signatures in the CMB sky that we can observe. Okay. So today we'll be talking about a model which is known as continuous spontaneous localization. So the wave function of according to the model, the wave function of the system will collapse automatically. So we do not need to have an observer. So inherent mechanism evades the requirement of the observer. So according to CSL model, we need not have to have an observer at the early universe. So this is a perfect model to fit into the early universe because we do not have any observer in the early universe to start with. Okay. So how to modify a Schrodinger equation? So this is not cosmology. This is basic quantum mechanics. Okay. So this first term is the Schrodinger equation. d psi by dt is minus IH bar H. This is the Schrodinger equation. But CSL modifies this simple Schrodinger equation by adding two different terms. First term is a stochastic term. This W field, this W is called the Wigner process. This is a stochastic term. By adding this stochastic field into this Schrodinger equation, it says that this is no longer a deterministic equation, but this is a stochastic equation, which explains why there are probabilistic outcome of a quantum measurement. A deterministic equation cannot actually tell you why there should be a probabilistic outcome of a quantum measurement. But if there is a stochastic field, that can explain why the outcome of a field would be stochastic. And then after that, we can see that the second term is a nonlinear term. And the nonlinear term breaks the superposition of wave function. So the two basic components of quantum mechanics, that the outcome would be stochastic, that the outcome would be probabilistic, had been taken care of by this stochastic field, and that there should be no superposition of wave function is governed by this nonlinear term. Okay. And also this gamma is known as the collapse rate. So the collapse rate should be higher for a larger object. So you can see that, so this collapse rate gamma is a function of mass. So this mass is the mass of the object with respect to the mass of a nucleon, and the heavier the mass is, the faster is the collapse rate. So if you want to have a wave function of a table, it will collapse immediately because it is much heavier than a nucleon. So a table is actually a classical object. Okay. And you can also model your collapse rate with a number of which is proportional to the number of particles in the system. If the number of particles in the system is higher, the collapse rate would be higher. So these are phenomenological models. So this has not come from a very underlying theory, but these are phenomenological models which you have seen in the nature, and we tried to construct a equivalent Schrodinger evolution, which is known as the CSA model. Okay. Now you apply these collapse models into the primordial perturbations. How can you do that? So then you have to go to the Schrodinger picture, because now you want to modify the Schrodinger equation of motion. So you have to treat this all these perturbations in the Schrodinger picture, and this scalar perturbations, which I have talked about earlier. So this is the scalar perturbations, and these are the metric perturbations, and this is the Mukhanov-Sasaki variable, which I have talked earlier. And this wave function or this perturbation actually follows a similar wave functional Schrodinger equation in field theory. And the Hamiltonian actually looks like a harmonic oscillator Hamiltonian, where this frequency now, as because the space-time is evolving, the frequency has a time-dependent part. This A is a scale factor, which was evolving the universe. Okay. And if you try to solve this Schrodinger equation, you can see the ground state would be always a Gaussian state, which is not surprising. And this omega k sitting here is of quite importance. In the next few slides, this omega k is actually like a inverse of the standard deviation of this Gaussian matrix, right? So you want to evolve, you want to change this Schrodinger equation. This is for the normal inflationary case, but now you want to apply your CSL mechanism. So you want to modify this Schrodinger equation by adding this kind of terms, this kind of stochastic and nonlinear terms. How does it look like? Okay, so before going to that, we have to define classicality in quantum field theory. How do you say that the quantum field has become classical? What is the quantity which measures the classicality of a primordial mode? And that is a difficult question. One way of defining classicality is through Wigner function. So Wigner function is actually a correlation between the position and momentum of the field. Position is actually like the field itself, and the momentum is actually a conjugate of the field. Okay. So if you calculate the Wigner function of the scalar perturbations, psi, star, and psi, you will get 4 Gaussians, 2 for the field and 2 for the momentum. But the problem is that the standard deviation of the field is proportional to 1 by this real omega k. However, so just the inverse in these 2 cases. For the momentum thing, this goes as real omega k, the standard deviation. But for the field part, it goes as 1 by real omega k. You can see from these 2 Gaussian factors. But if there is no CSL mechanism which is taking place, just the normal inflationary scenario, If we go to the super horizon scales, you will see that real omega goes to 0. That means this Gaussian functions, the standard deviation of these Gaussian functions would go to 0. They will start to behave like a delta function. And you plot this Wigner function, you will see that it will be high, because this is a delta function in the momentum space. The momentum space will be highly squeezed. So this is like a uncertainty principle, right? You know your momentum value very precisely, but you do not have any information about the field value. This is the uncertainty principle in quantum mechanics. That we know your momentum very precisely, but you have no information about the position. In this case, this is the field. But we do observe the field in the, so we see the field in the CMB sky. We do not observe the momentum. So by classicality, we should have got a precise form of the precise number for the field and not for the momentum. So the observation shows classicality in field direction. So we should expect the collapse model to squeeze the mode functions of the field in the field direction. So we can expect that the real omega k should go to infinity. Okay. So this is the expectations. But what we have, that real omega k in general case goes to 0. So it squeezes the Wigner function in the momentum space, but a classicality actually means to squeeze it in the field space. Okay. Now you apply your CSL mechanism into the scalar inflationary dynamics. So similarly, you have the functional Schrodinger equation. You add a stochastic term, you add a nonlinear term, and after that, the Hamiltonian will have a frequency which has a time-dependent part because it is an evolving universe, but also will become imaginary or complex because of the presence of this collapse parameter. Okay. So before we did this work, there were another group from Paris who applied this CSL mechanism into in inflationary dynamics, but they treated this gamma to be constant. So one of the drawback is that then we do not have this amplification mechanism which is needed. Okay. So they could not explain, they said that the CSL mechanism cannot explain the classicality. Then we went one step further and we said, let's implement the amplification mechanism. How can we implement the amplification mechanism into this model? First of all, the modes, we know that the modes when they were sub-horizon, they were quantum in nature. But then when they try to cross the horizon to become super Hubble modes, they will become more and more classical. So there is a sense of scale for the modes where the collapse parameter can work. So the collapse parameter can only work for the modes which are crossing the horizon or which are becoming super horizon. So the collapse parameter should have some sense of the time. And this is how we implemented. So we modeled our collapse parameter like this, so that it goes as minus k tau raised to alpha, inversely proportional to that. Okay. And we show that when this alpha parameter is between 1 and 2, we actually can squeeze the Wigner function into the field space. And that is the macro objectification. So we know precisely at what field value we should observe in the classical field, in a CMB. Okay. But the problem is that we achieved classicality, but the scale, the path spectrum, which was the observable, that became scale dependent, and that we didn't want. So the path spectrum becomes scale to make the path spectrum scale independent, we had to introduce another parameter beta. So this is the total scale dependent of the path spectrum, and by choosing the parameter beta to be nearly equal to 3 plus alpha, we can achieve a scale invariant path spectrum. Okay. I don't know how much I am doing good with time, but let me say something about the tensor perturbations as well. So as I said, there would be scalar perturbations and there would be tensor perturbations. The scalar perturbations, the macro objectification of that can be done by CSL. And we have shown in another paper that the macro objectification of the tensor perturbation can also be achieved through CSL mechanism. So this is the tensor perturbation, Hij, and tensor perturbations are actually, tensor modes are actually traceless and transverse part of metric fluctuations. They have two kinds of helicities, plus state and cross states. If you have seen the gravitational wave talks in recent days, you might have known that gravitational waves have two kinds of polarization, plus polarization and cross polarization. Each of these helicity states actually behaves like a massless scalar field. So whatever mechanism we have implemented for the scalar perturbations, the CSL mechanism can be directly implemented into the tensor perturbations as well. The assumption is that the CSL modified dynamics is essentially the same for the gravitons and the inflatons. Okay. So this is how after the CSL mechanism has been implemented, this is how the scalar perturbation and tensor perturbation look like. So this 2-point correlation function of the scalar perturbation is observed in the temperature fluctuations of the CMB modes, and the tensor perturbations, the 2-point correlation function of the tensor perturbations can be observed in the BB spectrum of the CMB modes. Okay. Now coming to the observables, this is how CSL have changed the observable. This is the scale dependence of the scalar power spectrum. And this is the standard result. And this delta comes from the CSL mechanism. Okay. So delta can be of the order of slow roll parameters. Okay. The tensor spectral index is also changed by this delta, not only the scalar spectral index, but also the tensor spectral index. And the consistency relation of inflation, which says that the tensor to scalar ratio has to be of the order of is equal to -8 times the tensor spectral index. This is the consistency relation of a single field inflation. Okay, that also gets modified. Okay, so the thing is that we can believe that CSL has played a role in the early universe, and all the observables can be seen as a part of the tensor perturbations. Okay, so hence a modified consistency relation and a blue tilted tensor spectrum can be a signature of the CSL dynamics in the early universe, and we still have to wait for the verification of the CMB modes, and that's it. Thank you.
Thank you, Professor Suratna, for such a wonderful talk. We all enjoyed it, and it was very informative. And now I would like, if there are any questions from the participants in the Zoom meeting.
Yeah, people can directly unmute and ask, right, Natasha?
Yes. Vivek, you can ask.
Okay, Suratna, I'm not from your domain. It was a good talk. I could say that, but I have some basic questions. When you talk of horizon or universe, are these qualitative or do they have any quantity associated with them? Like, how do you define an universe? What is the limit of that?
So the universe is actually infinite, but there is an observable universe that we see. So as you know that the information can travel at the speed of light. Nothing can travel faster than speed of light, right? So there is a boundary of the universe from which signals can come to us today. Okay. Beyond that, if the information has to come to us today, the signal has to travel faster than light. That cannot happen. So there is a boundary of the universe from which the information can travel to us, and that is the boundary of the universe. This is the causally connected universe that we see today. There can be universe beyond that, but that we cannot probe because there cannot be any signal that can go beyond that region, right? Because then the signal has to travel faster than speed of light. So that is the boundary of the universe. But actually the universe is infinite. There is no boundary.
Okay. And how about the horizon thingy? What was that?
So there are two kinds of horizon. I do not want to go into the, so the horizon is actually the causally connected region. That the boundary is called the horizon. So the portion of the universe which is causally connected.
Okay. So when you say universe, like Earth or all the planets and all, they come into the picture, right? So
Yes.
so do each like, is there any weighting associated with, let's say, Earth or Mars or like Moon? They have any particular amount of alpha, beta variable associated with them in making like the total contribution towards the universe? Or is it
I
there's
didn't
no?
follow your question very much, but
I'm saying that, let's say universe is X, which is total of all the planetary things and all that we can say, right? Let's say Earth, Mars, and Jupiter. So I'm saying that the contribution towards the composition of universe coming from Earth or Mars or Jupiter, is it same or is it variable?
when we're talking about universe, we are talking about much larger scales. So when you are talking about Jupiter, suns, and these are only the scale of solar system, right?
Yeah.
So
So
when you
do
are
they add
talking,
up? Do they add up?
very few, in a very less manner, because we are talking about scales which are larger than the galaxies itself, clusters of galaxies itself. That is the scale of universe.
Okay.
So we are talking about a much larger scale than the solar system scale here.
All right, that's too much for me to grasp, but yeah, nice hearing you.
Thank you.
Thank you. Professor Chari, would you like to say?
Yeah, I just wanted to know for the other audience, I just wanted to know what percentage of this universe is understood to a certain extent or completely, or what percentage of universe is yet to be unraveled.
So when we talk about the universe, we talk about different epochs. So if you talk about the present epoch, and if you talk about the matter content of the present epoch, we only know the 4% of matter content of the present epoch, which is consists of the standard model of particle physics. Beyond that, there is dark energy, there is dark matter. We have no idea about this kind of components. Okay. So to answer your questions, okay, if you talk about the present universe, we only know 4% of that, and rest of is still unknown.
Thank you. Yeah, Lokesh.
Yeah, hi Suratna. Very nice talk. I just wanted to get a clear picture of the connection between the inflation and the cosmic microwave background which you mentioned, because there are many stages in between, and then how you mentioned that they are directly connected or somehow. So maybe if you can just
I actually stopped sharing my screen. Can I share my screen again?
Yeah.
You are correct in saying that. Let me show you which. Yeah, so this slide. So this is the perturbation in the scalar field, which was seeded during inflation. Can you see my screen?
Mm-hmm. Yeah.
And this is the temperature fluctuations. And this transfer function encapsulates all the physics that goes from inflation to formation of CMBR. Okay. So this is quite an amount of physics, and that requires modeling of the universe itself. But this transfer function encapsulates all the information that goes from going from inflation to formation of CMB. So similarly, you can see that the power spectrum here, the 2-point correlation function of the power spectrum here, which is caused by inflation, multiplied these transfer functions, which encapsulates all the physics of the universe beyond inflation till the formation of CMB.
Okay, just to carry forward it. Do you know this function already, or I mean, how you put inputs into that function?
We know this function quite well because we know how the universe has evolved. So according to the Big Bang theory, so we have probed till this much era. So you can see where when the age of the universe was 10 raised to power minus 10 seconds. Since then, the physics is known. So we can actually calculate this transfer function. This is a very complicated form. I didn't put it in the slides, but if you, but the assumption is that the universe has evolved according to the Big Bang model. If there is any other model, then all this transfer function will change.
Right.
Okay. Thank you. Is there any other question? I do not see any raised hand. So now I will hand over to Professor Vandana to check if there are any questions on YouTube.
Thank you, Natasha. First of all, very, very nice and very informative talk, Suratna, and it was very heartening to see that you actually spelled out a lot of complex things in so much nice details. There are also some appreciative comments on the YouTube. We have. I must also add that we actually have very committed YouTube audience. They always, a few of them always attend all the talks. So there is one of them is Abhinav Chaudhary, and he has a couple of questions. So I think we have time to take two. So the first question is rate of expansion of universe even faster than the speed of light?
It can be. There's no problem in that. Because during inflation, you can see that it is exponential expansion.
Yes.
Right? Yeah. So there's no problem with causality in that. Okay. The information cannot travel more faster than speed of light.
Okay, thank you. And next question is, are cosmic inflation and dark energy connected?
There are models where people try to connect cosmic inflation and dark energy because both are accelerated expansion phases of the universe. Inflation is the accelerated expansion in the early universe, and dark energy dominated phase is the accelerated expansion, not accelerated expansion. It is accelerated expansion in the late universe. So the dynamics are quite similar. So people have tried to model this inflaton field, which can actually play a role as an inflaton in the early universe, and then it remains in the universe as a dormant field, and at later stage it can become a dark energy. So yes, that people have tried to connect these two regions.
Thank you. And I think there is this last question, which also is a good question to end the talk, I think. Will cosmic deflation also take place at a certain period of time after the inflation?
No. There was no deflation. It always kept on expanding.
Thank you, Suratna. Thank you, Natasha. Back to you. Natasha, back to you. Yeah.
Okay. Why this temperature fluctuation arises at all?
The temperature fluctuations was seeded by the fluctuations in the by the fluctuations in the inflaton field. Those fluctuations were seeded by. So there were fluctuations in the inflaton field. Those fluctuations get implemented into the fluctuations in the background metric. Those background metric fluctuations then seed those fluctuations in the CMB at a later stage. So first it goes from T mu to G mu, then G mu to T mu.
Okay. And in one of your slides, you mentioned that this CMB photons are polarized.
Yes.
Do we know the reason why?
Yes, we do know the reason for that, but it is so complicated that I didn't put it in the slide.
Okay.
Yes.
And
definitely we do know the reason why it should be polarized. So it was the theory first, Theoretically, people have came up with the fact that the CMB photons has to be polarized, and then it has been observed. So we know the reason why it should be polarized.
Okay. And by any way, have you tried to compare your model with the experimental results?
Yes, I think I was not very clear in mentioning that, but the last slide was about that.
Okay, okay, where you showed the
yes, all the observables.
Okay, okay,
Yes.
okay. Thank you. So this was very nice talking to you and knowing about the inflation in cosmology. Okay.
Thank you.
Professor Vandana, you want to say something?
Now we would like to thank both the speaker for a wonderful talk and you and ICB Rampur for organizing this talk. So thank you very much. And as you know, the talk will remain available on the YouTube for all the interested viewers. I also urge all the students to visit IPA webpage to know about future activities. So stay safe and thank you.
Okay. Thank you all. Thank you all participants for joining. Thank you, speaker, for the very nice talk.
Thank you.
Thank you all. Bye.
Bye. Bye-bye and hope to see you all in person soon.